All right, so welcome back, everyone, to the Bayesian statistics and cognitive modeling seminar. So the last week, we basically discussed or introduced the simple Rescorla-Wagner in the bigger context of reinforcement learning. And what we started off was the two-armed bandit task. So where we imagine that there are two slot machines or bandit machines in front of you, and each of them, they are associated with a reward probability. So reward probability basically means how often when playing this machine, it will return you the reward. So let's say between the two machines, one of them is better and the other one is worse. It is a fact, you know that one is better, one is worse, but you don't know which is better, which is worse. So better means with higher probability, worse means the reward probability is low, okay? And what you're supposed to do in terms of figuring out which is better, which is worse, the only action that you can have is basically, well, you can play with it. What you can play here is basically pull up this lever and then to see what outcomes or consequence you will be able to observe. And then, for example, if you play this one, then you observe reward, then basically, very likely that you will repeat your previous success because you did it, it was successful, and why not doing that again, right? But if you play it, then you lose, perhaps you want to switch to the others. This is like a simple strategy, which is called win, stay, and lose shift. I think you also read it from the paper that you're about to review. And this strategy doesn't really involve any value updates. This is basically kind of a heuristic strategy. If you win it, you just repeat your previous success. If you lose it, perhaps switch to the alternative with the hope that the other one is better than the previous one. But maybe if you are unlucky, you play this one, you lose. If you play this one, you switch, but you also lose. Maybe you will get confused, maybe to switch back or not, right? This is a kind of an interesting scenario. And why this could happen? This actually happens. If you play this one, you lose. If you play this one, you also lose. This happens because the reward probability here plays some function. It functions here. So even though, for example, from a bird eye view, if we know that this one has 80% reward probability, this one 20%, you play this one, you're not in the 80%, you're in the 20%, and then you lose, and then you switch to the other one. But this one, 80% you lose, then you also get a loss, right? It happens a lot. So it then requires you to really learn to use the updates, to use the feedback to update your learning strategy. Then the learning strategy here is to predict or to anticipate how valuable each option or each slot machine is on average. So here the strategy, what we had is like, well, first of all, the task, right, as introduced. So you repeatedly play with the two machines. You choose one of them first, and you play, and then you see the action, and then you see the feedback. After the feedback, you learn, and you update your evaluation, and then play it again. So your strategy is when we were trying to tease apart or differentiate, decompose the steps in this decision making in the process, we would imagine that in the first place, you predict which one is better, which one is worse. After the prediction, you make your action according to your prediction. And after you see the feedback associated with your action, you will be able to learn from the feedback. And there are multiple ways to learn it. And one way that we were focusing on is the Rescorla-Wagner value updates. The idea is arrow-driven learning. The arrow basically here means the difference. There's a term called prediction error, and then the error, prediction error, equals to the amount of reward you actually observe and the amount of reward that you predict, you anticipate to observe. So here, this is again the conceptual idea or theoretical framework that quantifies everything that we are trying to explain to you. And here's again the task. Usually we don't show participants like the bandit machine, we show them abstract symbols, or you can call this kind of fractals. Some other people also use like different characters from different languages, like Japanese, Chinese. The characters are used a lot in like Western countries, and then also maybe some other letters that I don't even know. Because they're abstract, they don't even have a specific meaning. So that's why people use them as stimuli. So here we could also name those phases or like terms or the screens. And there are only three screens, which is pretty straightforward. And here in the beginning, we try to, we just show participants the two choices, and they're supposed to make an action, make a choice, make a decision between one of the two. So choosing one of the two, choosing one between the two options. And after choosing the option here, this one is highlighted. After choosing, the outcome will be delivered. The outcome here is related or associated with the action. We also try to ask ourselves, if we were to do this, if we were to perform or to conduct this experiment, what do we know? And we could imagine that if you are like the experimenter, if you are a PhD or master student who is currently running the experiment, and each time, not only you have to care about if the participant is paying attention to the button press, if you are in the lab, you would also have to pay attention to or take care of the data collection, because if after the button press, everything is not saved into the computer, this is wasted, right? So every time if you do experiment, you also have to save your data. And then this is called usually log file, just to log everything, log what happened during the task. So what happened in the task? Just choices and outcome, right? Which option the participants chose during the task on a trial by trial basis, and which outcome they observe also on the trial by trial basis. And then the action and the outcome and the action here, they are apparently associated. This outcome should be the outcome, the observed outcome after making this action. Additionally, we could also have reaction time, response time. So after they have seen the two choice options, between that, from this presentation to the moment where they initiated, they press the button. So this is the definition of reaction time, right? So here we could also measure how fast or how slow each participant is playing. So maybe in the beginning, we don't, in the model, we don't even analyze data, but just to let you know, to think about that. So if in the beginning, let's say the participant is not so familiar with the setup, and they just see the blue and yellow, which don't mean anything to the participant, maybe they will have to be a little bit careful. The response might be slow. But maybe let's, for example, say there are 100 trials, and at trial 80, 81, it is already quite late, like in the course of the environment, in the experiment. And participants, if they are smart enough, they don't have to be so smart. If they are just trying to pay attention to what happened by selecting one of the two choice options, they will be able to figure out which is better, which is worse. And then in that case, they will be pretty fast in terms of which option they will be choosing from. So the blue or the yellow. And this also depends on the difficulty of the task. So for example, there's blue, there's yellow always. Let's say the blue option is having a 95% reward probability, and this one loses 95% of the time, 95, right? This means this is easy task. This is nearly deterministic. It is nearly, if you choose this, it's nearly almost of the time, almost every time you will get a reward. And people can just press. This is very easy. This is easy task. And in another scenario is that, well, 50-50 is nothing you can learn. And 50-50, usually people don't do that in the environment, in the experiment, because how can you analyze the data? It doesn't really matter so much. It doesn't make sense so much. So a more informative but difficult task is 60 and 40. 55 and 45, honestly, is still quite difficult to learn. 40 and 60 it is learnable. This is not a word, I guess. People are able to learn from a 60-40 combination, but this is quite difficult. So in 60-40, this combination, this is a difficult task. Maybe at the end, nearly approaching to the end, even at that time point, people are still a little bit slow because that's a difficult task. At the end, even at the end experiment, people might still be confused. I've seen this. I used a 60-40 task earlier. The average performance is really worse. Some people, they don't even learn from 60-40 environments. So the reaction time is remarkably longer or slower than the, let's say, 80-20 experiments. 80-20 is a good one. 90 is too easy to learn. You don't learn. You just press and then see, and then you just stick to it. You don't even have to learn too much from it. All right, so there's a question. So in this 50-50 scenario, is there probability of guessing right by accident also incorporated into the model somehow? Yeah, kind of. Yeah, this is nearly guessing, right? Whatever you do, you can earn something, but it's difficult to figure out which is better, which is worse, because indeed, the reality is that there's not a better option. They are the same, equally worse, let's say 50-50. Does that answer? Kind of. All right, so then what we can do before entering the modeling analysis is to analyze the accuracy. So how often the participants is choosing the better option. Imagine that if there are 100 trials and the experiment is 70-30, this is okay-ish, not so difficult, not so easy, but people are able to learn from it. 70-30 is a good one most of the time. So let's say there's a 70-30 experiments, and we could analyze how often the participants is choosing blue. Suppose blue is the better one with 70% reward probability. And if you read from the literature and the reward probability, it is also called a reward schedule. So usually it's written this way, I think. So 70 with a colon, 30. So this is called reward schedule. This means what? So this means actually multiple things, even though it appears to be as simple as 70-30. So it means, let's say there are two choice options, one blue, one yellow. This basically means the reward probability P of B to win, what is win now? This is win, euro. The reward probability of choosing blue is 70%, 0.7. And then the reward probability of choosing the yellow to get the money is 30%, okay? This means that both of them. This is not trivial because it is not a coincidence that they sum up to one, because the experimental design is designed this way that if one action, the reward probability is 0.7, then the other one is 0.3. But it doesn't have to be this. It doesn't have to be this. So some of the experiment, they use a drifted reward probability. So let me try to unpack this idea to you. So let's say this is trial, okay? This is trial. This is reward probability, just P of getting money. So if suppose there is no reversal, reversal means the reward probability also changes. Better becomes worse and worse becomes better. Let's assume no reversal, just no reversal. What the reward probability looks like? This is a constant line, right? This is a constant line. Let's say this is 0.7. And the other one is 0.3, for example. This is blue 0.7, and then the other one is 0.3. Okay, this is a complementary reward probability. P of blue plus P of yellow, it becomes 1. And there are some other scenarios. So similar graph on the x-axis, this is the time, the trial. The y-axis, this is the reward probability. Okay, so percentage. And some people use a drifted reward probability. What does that mean? So here, let's say it changes with kind of drift. This is drift with some randomness, with some slow noise, drifting up, drifting down, drifting up, drifting down. Okay, good. Perhaps there is another one. So usually not so correlated, or anti-correlated. No, there's no backward possible, not possible. Okay, anyway, here is like this, okay? So for example, if you correlate the blue curve, this looks correlated, but assume that there is a perfectly uncorrelated drift reward probability. You calculate the time trial, not the time trial, not this, the time course of the trial, time series of the trial. So that becomes 0. So then these are uncorrelated. If you learn the reward probability of the red, doesn't mean that you know anything about the blue, because they are uncorrelated. There's no dependency between blue and yellow. It's always that at each time point, here, one is always better than the other. Here, or maybe in general at this stage, from beginning to this stage, the red one is better than the blue one, okay? And then this stage, or maybe until here, the blue one is better than the red one. And then here back, the red one is better than the blue one. And also, they don't sum up to 1. So the probability of blue and the probability of red in these two occasions, they don't have to sum up to 1. And this is it's not an easy task, but it's learnable. People are able to learn from it. And you might wonder why people are using this kind of drifted version of reward probability than the other one. Well, it is because this makes the task more dynamic. So here, this kind of version is good, but perhaps too easy to learn from. And then this one is like, at the beginning, maybe 0.7, and then up to 0.75 a little bit, and then 0.8 a little bit, and then back to 0.7. It appears that it changes, but on average, it's a good one. So you could imagine this is on average a good one, around the 0.7. Maybe this is on average a okay-ish one, point something, 0.5. So here it is more dynamic. So it's more engaging. People always have to learn and relearn to increase the uncertainty of the task, to make participants more feel more engaging. Good. Okay, there is still a question. I think I didn't answer that properly. So if there are only 2 symbols to choose from, yeah, and then it is like 40-60, good. Isn't there a possibility that it seems like the person learned right twice when in reality they only randomly guessed? I guess it's possible to model this kind of scenario in the analysis. Or maybe do you want to speak up? Hello, Martina.
Hi. I was just wondering if that's a thing that's normally done or not.
Not quite, I guess.
Okay, thank you.
Okay, thank you. I think I now know what you mean. I will tell you later, but because we are not there yet. I think now I know what you mean. Yeah, I will write that down. So to explain this to you. All right. Great. Then we move on to the next point, which is to learn like the model. So how to quantify the learning process in the 2-armed bandit task. So what we had is a simple Rescorla-Wagner value update learning. So what we have is we focused the last time on the cognitive model part. So here we are trying to explain how the values of the option of value of blue and the value of yellow, they are updated using the feedback, using the prediction error. So those are the cognitive model, the cognitive process. And after the models, after the values are updated or calculated, how this value can be related to the actual action. So we calculate the value of blue, but how do we know or how likely the participants will be able or will be more likely or less likely to choose blue on the next trial? So how can we change or turn or convert, translate the value of the options, value of blue or value of yellow, to a probability of choose each of them? The probability of choosing blue, the probability of choosing yellow, how these are connected. And then this relates to the observation model that we didn't talk about last time, but we will talk about that today. Also, that is the point I could try to explain a little bit more to the Martina's earlier question. So here is like one more time to recap what we have learned from the last time, Rescorla-Wagner. What we could imagine that in the like human language, oral or written verbal version of the model is like the expectation on the next trial equals to the expectation on the current trial plus a learning rate weighted reward prediction error. And the prediction error is again the difference between what you actually get and what you think you will get. So here to quantify that, and we changed this verbal description to a more precise and mathematical equation. So here, the reward prediction error, the PE, is calculated just by the literal meaning, the actual reward minus the previous expectation or the current expectation, depends on how you interpret the T. Let's just say T minus 1 is the current one, and then T is the next one. So here, after the reward prediction error is calculated, it is then entered into the first equation multiplied with the learning rate to update the value signal, right? So here we could understand that it's like this is old one, this is new one. We want to change from the old to the new, and how the old one will be changed, what will be the added part. So this is the added part. The added part is as simple or as straightforward as the learning rate, multiply that with the reward prediction error. Reward prediction error is, just one more time, the difference between what you actually get and what you think you would get. So the learning rates is the free parameter, is like the slope and the intercept parameters in the regression model. We don't know the reward, we don't know the parameters of the slope and the intercept. They are part of the model. They are the important recipes or components or elements of the model. We want to know them. So remember the idea of doing modeling, data modeling, we connect known and unknown, and then we want to use a proper likelihood function. So in the globe example, if you still remember that, we have like 9 times of like the globe tossing, and we observed 6 times of water. There's an unknown parameter, that's the proportion of water covering the entire Earth. That is a parameter. And we use a binomial likelihood function to connect the known and unknown, and then to estimate this parameter, right? So this is the idea of parameter estimation or model estimation. And here, the cover story has changed, but the underlying idea is the same, is identical. So here we do experiments. We ask 10 people maybe to come to the lab, and each of them, they have to do button press 100 times, choose blue and choose yellow. And those are the data. Those are like the coin flipping or the globe tossing data from the previous example. And we also assume that those are the learning process. So those 10 people's learning process, they are quantified by a parameter called learning rate. So this is like the proportion parameter. We are interested in it. We don't know it yet. And we want to establish a likelihood, a connection function that links the known and to the unknown. So here the alpha, the learning rate, is the free parameter. Similarly to the proportion parameter from the globe tossing or the coin flipping example. The last time we also had a simple calculation regarding how to interpret or how to better understand the learning rates. So the best strategy here is to make it more concrete. Otherwise, it is always quite rather abstract to think about this kind of mathematical notions. So to make it concrete, we can just change the variables into numeric values, and then we are really able to understand everything, right? So suppose that we are like fixing the parameter to be 0.9. Suppose basically that we know the parameter learning rate is 0.9. And how does the value update works? So the first step is actually to define the initial value, because we have to, the value update has to have a starting point. So we basically initiate the value of the two options to be 0, because at the beginning, they don't really, participants, they don't really have any idea about the two choice options. So maybe their value regarding blue, regarding yellow, both of them equals to 0. At the very beginning, this one is 0. Maybe let me just try to write it down. That's much more easier. So let's say the value of the first trial at the beginning equals 0. And then let's say after making the choice, the reward is 1. Okay, so what is PE? PE is just small letters. PE basically equals the actual reward you get minus your previous value, right? Then what this becomes is 1 minus 0 equals 1, okay? So PE is then multiplied with the alpha plus the value of the first one, and then it becomes the value of the second trial. So then what is this? V of 1, we defined it is 0, right? What is this? 0.9 and multiplied with a 1. So here, this is the 1, the PE, okay? And the entire thing, just 0 is 0, this is 0.9 and then 0.9, okay? So the entire calculation here tells us V of 2 now equals 0.9. Good. And we can do another round of the value update. Let's say now we have value of 2 equals 0.9. Let's say the participant is really lucky, and he or she, the second outcome is also a 1, okay? So what is the PE? So one more time, what is the PE? PE is the actual reward minus the expected reward, or the value, or the anticipation, or the prediction, however you call it. This is one more time. And that is used to minus 0.9. This one is a smaller one. This is 0.1, okay? You get a small prediction error. So why you get a prediction error as small as 0.1? It is because you are already pretty close to the actual reward. So then if you would expect that you will get a reward and you actually get a reward, there's not so much mismatch, right? Your expectation is realized in a way, let's say. There's no surprise. So then the reward prediction error, the mismatch is small. So here you have a 0.1. So then how do we update the next value? So the value of the next trial, the V of 3 equals V of 2 plus the learning rate multiplied with the PE, okay, good. What is V of 2? V of 2 is like here, 0.9, 0.9. And what is learning rate? Learning rate is also 0.9. This is as the definition. So what is PE? PE is 0.1, okay, 0.1. And then this equals 0.09, and you do it, and then you have a 0.99, right? Good. So after consecutively observing 2 positive feedback, your prediction becomes already super close to the action, to the value. So the value is 1. If you win, you get a 1. And if you think that you go to the next trial, if you still get a win, what is the prediction error? Super small, right? 1 minus 0.99 is 0.01. This is super small prediction error. But now let's assume that the person doesn't really go to the lucky area so often. let's assume, let's just kick this one here. Let's assume the person get a loss on the third trail. So how do we do this analysis or to this update? So V of 3 equals 0.99 already. Good. And then let's say the R of 3 equals a -1. So this is not a win, it's a loss now. Now you could imagine that this is a huge prediction error, right? I'm now expecting I will get a reward, and I really have this kind of belief I will get a reward. But what is the reality? It is really disappointing. I get a loss. There's a huge mismatch. I'm so surprised that I got a loss, even though I was thinking I will get a reward. So this is a reward prediction error, large reward prediction error. And there's also a sign here. So the reward prediction error is negative in this place because what you actually get is so much worse than you think you will get. Let's do this calculation. So one more time, PE equals R of 3, like minus the V of 3. What is R of 3 is -1. And what is V of 3 is 0.99, but then there's a minus sign. So here, this is like 0.99. Okay, minus. In the end, you get a large -1. So you get a 1.99. Reward prediction error. This is a large negative prediction error. So how to update the value? So here you have V of 4, right? V of 4, let me erase these things. Okay. The V of 4 is the updated one because you are here. V of 3. After observing a negative feedback, what's the value will become? Okay, PE. So this is a good one, 0.99 in the beginning, but then you have a 0.9 learning rate multiply with a negative reward prediction error. Okay, good. I don't know what this value equals to. I need something calculate for me. Oops, not there. Right. I don't know if I have it. Okay, just super slow. But anyway, let's roughly calculate this. We could try to, let's say, this is nearly -2, right? Let's say if this is -2, what is the entire thing? This is like minus like 1.8, right? More or less. And then there's the positive thing. So what you actually get is still minus 0.9 something. I don't know. Maybe this is entirely wrong. We have 0.99. This is the previous value, and then we have the learning rates. We use that to multiply with 1.99, right? Okay, so I'm not so far away from that. It's minus 0.801. Okay, good. We have it. It's not minus 0.9. This one is minus 0.801. Okay, anyway, this is our calculation. So now you see that how the values are updated. And then if the next trial you get a reward, and what is the prediction error? Then that is a huge positive reward prediction error, right? Because you use 1 minus a minus 0.8, you get like a 1.8, positive 1.8 prediction error. That's a large, because here you get a loss, you think, well, this is not a good option, I won't get a reward next time, but I get a reward next time. What that means, that means the reality is way better than what I think. This is a large positive reward prediction error. And then if you use that one to update your value, it becomes better again. It changes back to the positive domain. And then you can do this for ages from the first trial to the last trial. And if you want to kind of plot this idea, this is how that looks like. So here, first one is 0, initial value, and then 0.9 after the first evaluation, and 0.9 becomes 0.99 if you remember the idea that we calculated. So because the reward prediction is getting closer and closer, if you always get a positive feedback, then here there's no reward prediction error. So the value update also doesn't happen because there's no difference, nothing to be updated from in this case, until you get a negative feedback. And then the value will have a huge drop, like the one, as if the one that we calculated. So what we had is minus 1.8 something. So minus 8, minus 0.8, okay? Minus 0.8 here, roughly. That is a huge negative reward prediction. And after the value update, the value becomes initially super close to the possible positive consequence to already the negative counterpart. So now you would imagine, is that a good thing or not? That we explain this idea. So if like, yeah, you're in a relationship, if every time everything is good, but just one time your partner is not really responding to your message or whatever, it might be that the person is in a bad mood, but perhaps you are overreacting this. You might think that, well, what did I do wrong? Something like that. So do you think that's a good idea or not? So maybe it's not a good idea, right? You have to like tolerate this kind of uncertainty. So here we know that even though after you have seen multiple times of positive feedback, even just one time of negative feedback will just turn the entire story. This is not a good idea. So what you have learned, all of the positive experience or memories that happened in the past, you just forget about it. You didn't remember that anymore. And you always care about the most recent negative one. So the most recent negative experience really has a huge impact. This is what that shows on this graph. But that doesn't mean this is a good thing, because this is a probabilistic environment. 80% of the time you win, 20% of the time you will lose. So all of the 20% of the time, they are probabilistic losses. And you actually have to try to ignore them because they are the probabilistic loss. This is random. Because of the randomness, you lose sometimes. So would you imagine that the occasional loss will change how you learn? It's actually, you try to ignore them, right? So the occasionally happened losses during the learning, you really don't have to care about them too much. So then what we can do is like, we could do a few more simulations to see how the curves change according to different magnitudes of the learning rates. So the one here is 0.9 that we have seen already. And then as the color goes from dark to a little bit lighter, so you see how the curve changes. Essentially, the reward prediction error goes both ways. If it's is high, it updates positive experience very high, and it also updates the negative experience pretty high. If the learning rate is slow or small, then that updates both the positive experience a little bit slower, but at the same time, the negative experience, the update is also slower. So just let's compare these two numbers, the two dots on the graph. So this is the first negative feedback that the person has encountered. Previously, everything is good, just positive and positive and positive. If the learning rate is large, this will be the updated value, which is super negative in this case, because -1 and 1, those are the possible limits, the lower end and the upper end. And during the learning for a occasion where the learning rate is 0.3, so you can't even see that, but there's the turning point. Okay, this is the number. So after one time of negative feedback, the magnitude of value, so here's value, right? The entire value is also positive. So the person basically learns or memorizes all of the possible positive histories in the past, even though one of the most recent feedback is negative, the overall calculation, the cumulative overall calculation is still positive. So it's still a good thing. Not so much overreaction, or oversensitivity to the negative punishment, negative consequence. So perhaps kind of point 3 is okay here because it considers the probabilistic nature, and the occasional negative feedback doesn't impact so much the learning. So now you would imagine that so the negative learning rate, or not negative learning rate, doesn't exist. Not negative learning rate, small learning rate, 0.3, for example. 0.3 learning rate seems good and seems okay here in this particular case, but is there a place for a large learning rate? So what are the possible scenarios or where the large learning rate is a good one? So here, what we would imagine is like this. Let me just try to draw something. Yes, not enough white space. So this is trial, okay? This is reward probability. If we have a 80-20 scenario without reversal, so the reward probability is a constant line, and this one I showed you earlier already. But because everything is probabilistic, so 80% of the time you get a reward and 20% of the time you get a punishment. So let's just draw a parallel graph. This is time, always trial, and then this is the actual outcome. The actual outcome that corresponds to the reward probability is not a constant line, right? Because 80% of the time you get a win and a loss, maybe another loss, and then win, loss, win, right? Loss, win, okay? This is the outcome. So if there are 100 trials, so 80% of the time here it is a 1 and 1. And the other 20% of the time, this is a negative 1. Okay, good. And what is this telling you here? This tells you that this is a stable environment because the reward probability doesn't change. Just there is sometimes, from time to time, the randomness, the probabilistic negative feedback, the randomness. But what if we have another scenario? We have like, let's maybe draw here. The reward probability getting euro is changing from time to time. In the beginning, maybe at 80% of the time, and then 30% of the time, 70% of the time, 40% of the time, 90% of the time, okay, whatever, just goes up and down, ups and down. Okay, good. This is the reward probability of one option. And then the other option, let's just keep it easy, just one minus this. But then just the other way around, upside down. That's the reward probability of the other option. So this is for blue, and the upside down version is for the yellow, okay? So what is the outcome here? If you draw this kind of thing, if you try to simulate it, what can it look like? It changes like very rapidly, I would imagine, actually. I can't even draw this because like there's also the probabilistic nature in this kind of field. So it's basically pretty noisy. And we imagine that here in the left scenario, learning rate 0.3 is kind of okay-ish one because it doesn't really overreact to the negative feedback. It tries to learn to accumulate all of the positive experiences from the past. So here, let's say around here, let me just give you a few examples here. Let's say up to this point, I get reward 1, 1, 1, 1, 1. Because of luck, for example, I get many of the wins in this case, also because the reward probability is a good one, is a high one relatively. And then after that, I start to get loss. And then maybe one time of win and then another of loss, okay? And let's just focus on this small section of the trial. So let's say if we have a learning rate of 0.3, so then the value will be just accumulating, right? As we have seen from the past. And then it goes down a little bit because the learner rate is small. Even though there is a negative feedback, it doesn't drop so much, okay? But is this a good thing or not? Perhaps not, because it doesn't really give you a informative information enough so that you could be able to realize there's a reversal already. Does that make sense? And at this stage, if you have a positive, if you have a large learning rate, then in this case, it increases quite rapidly. But then as long as you observe perhaps at least one negative feedback, your value will be dropped. But is this good or not? This is good, right? Because it will help you to be able to realize or to find out, to work out the reversal might happen here. The reversal might happen from a good reward probability to a worse or poor, bad reward probability. So the long story short, if the environment is stable, most of the time, a low learning rate is more preferred, okay? BLE, okay? And if the environment is changing, or in some literature, this is called volatile environment. This term comes from stock market. It changes a lot. So that's a volatile environment. It's a changing environment or unstable environment. As you can see here, it goes up and down, multiple times. This is a volatile environment, changing environment. And in this changing environment, most of the time, you would imagine a large learning rate is more preferred. How large? I don't know how large, maybe 8.8, I don't know. Okay. So why am I telling you that I don't know? Because I actually don't know. It is because the optimal learning rate, it exists, depends on the model. You could be able to find it out. And the optimal learning rate depends on many things. So the one I showed you is one factor, if that is stable or if that is changing. Stable versus changing. This is already one factor that will affect the optimal learning rate if that exists. This is one factor. What is another factor? The other factor is the actual reward probability. So stable here. So how stable? 0.9 is stable, good. But 0.6 is also stable. But as I told you earlier, 0.6, 0.4, this is a difficult task to learn. So what is the optimal learning rate here? Those, in these two scenarios, the optimal learning rate, they do differ, okay? And then the changing here, well, we could have one scenario. It changes from 0.9 to 0.1 to 0.9 to 0.1. This is a changing. But in another scenario, it could be that 0.6, 0.3, 0.7, 0.4, something, just lower, relatively lower, okay? This is 0.9. This, the highest is 0.8, for example, with changing, with reversal, but the magnitude is different, slower, smaller. In these two scenarios I'm showing you, the optimal learning rate, they also differ. So what is another scenario that you have to consider? This is actually the number of trials. So if I show you 0.9, 0.6, if I show you 100 trials, you are, in this case, I guess you are pretty confident afterwards. You will be able to tell if this is a good option or not, because most of the time, the outcome is nearly deterministic. If you see that, most of the time, 90% of the time, you see the more frequent outcome, either win or loss, if you choose the other one. And if I show you 100%, 100 trials of 0.6, it's difficult, but still you are able to figure that out, right? You have enough evidence or enough data to look into. But let's say I now cut the trials, not 100, but 10, okay, 10. How many reward you will be able to observe here? Maybe 9, maybe 8. So it depends on the probability. On average 9, but maybe in one occasion, you have 8 times of reward and 2 times punishment, but still informative, right? 8 out of 10, good. But maybe here, because of probability, maybe what you observe the actual sequence is 5 times of win and 5 times of loss. What to do? This, I don't know, right? This is a difficult one. So the optimal learning rate in these two scenarios, they're also difficult. Here, the same thing. So if we have a lot of trials, then that means the reversal just goes on and goes on. But if we have not so many trials, maybe what we look at is only here. Like in total here, 10 trials, what's your take? It's difficult, right? So let's maybe just give a summary. So what affects the optimal learning rates? So the optimal learning rate, one is the environment, meaning stable versus changing. Two, the actual reward probability. So 0.9 versus 0.6, for example. And then the last one is number of trials. Okay, how many trials do you have? 100 versus 10, for example. There are some others, I guess, but these three are the most like influential ones to try to help you to determine the optimal learning rate. So now the next question is, let's say this is fixed. Okay, I want a stable environment. I want to have 80-20. And I do have 100 trials. When those are known to us as researchers, how can we determine the optimal learning rates? So the answer is to do simulation. I think I'm trying to show it to you on the next slide, but up to this point, any questions? I put these things here for you to memorize what we have discussed. Oh, good. Okay. Perhaps for those of you who are really into these mathematical formulations, I can just tell you a little bit more about how this learning rate works. So we have seen this equation that looks okay. But it is actually possible to rewrite the v of t as a function of the initial value to like all of the outcomes that you will encounter since the beginning to the point of your current trial. So what that means? And so let's say we have v, right? We have v of t equals v of t minus 1. Okay, learning rate, good. The reward, t minus 1. Okay, minus the v, this. Okay, good. So what we can do now? So we can change this a little bit to what? To, let's say, we have alpha multiply with the reward. Oops, t minus 1. Okay, this is this term. And we have the v. We have 1 minus the learning rate, okay? Multiply the v t minus 1, okay? Just to group the variables, like from earlier arithmetics you learned from school, just to change it. Nothing really fancy here. So then what is t v minus 1? V of t minus 1 equals v of t minus 2 plus the learning rate, the reward, t minus 2, then minus the v of that. Okay. This thing can be entered into this one, right? So then the entire equation is unpacked. It becomes longer and longer. It's getting longer and longer. So each time the v can be written as a function of the previous v. And then the previous v, the value can be written as a function of the even previous value. And that one can be written as a function of the one even previous to that. And you can do this until, you can do this for multiple times until you have p of the v of 1 or v of 0. Okay, here. you do it. If you are at 1220, the value of 1220 equals to the value of 19 with the updates. And then the v of 19 equals to some function of 12, value of 1218, and then the 1217 and 16, and goes back into the history where everything began. That's v of 1, the value of the first tries. So you can do this kind of things a little bit more like iterative, okay? And in the end, what you get? In the end, you get kind of this term. So if you have this term, so what you have to try to understand is this term, okay? Well, together with the alpha, together with the alpha. This is actually why the reason, the most recent one counts a lot for positive and large learning rates, and everything happened in the history that you can consider where you do not have oversensitivity to the negative feedback when you have a slower learning rate. So this is actually the reason. Well, I think conceptually you understand now from my description, but mathematically how this makes sense, it really depends on this term. So this very term here. And this term, I guess, is also difficult to understand because there are so many stuff. So what you can do, the best idea is, again, to visualize it, to make a plot. So how can you plot it? You can actually plot it. So with this bar graph, I think graph, everything will become much more clearer, I think. So this is t, the current trial, t minus 1, t minus 2, t minus 3, until the 7th trial in the past that had happened. And then the y-axis, what is that? That means the weight of the outcome that is influencing the value update, okay? The outcome, the actual outcome, they are just minus 1 and 1. But how important they are when values are updated using the Rescorla-Wagner evaluation. So if we have a positive and large learning rates, I don't know why I'm constantly saying positive, they should always be positive. So if we have a large learning rates, so the value is updated from mostly the current trial, okay? The outcome from current trial that counts a lot. And already go to the trial 1 back, the outcome really doesn't function so much already. And 2 trials back, the outcome, whatever that happened, positive or negative, it doesn't really show much influence or impact towards the value updation, towards the value update. But I guess if we have a smaller learning rate, for example, here, so even though the most current or most recent outcome, that doesn't count so much, but that still counts something. And at the same time, everything happened in the past, here and here and here and here and here and here, right? So all of them, they have a non-negative, non-zero weight. So that means that outcomes that happened in those past, they could be accumulated. They could be carried over to the current trial. So in other words, if they are positive, the positive experiences can be taken over to the current trial. Not that you forget everything happened in the past, which is the case for a large learner rate. Okay, does that make sense? Kind of. Maybe this is a little bit too much, but just conceptually, if you are with me, then I will already be very happy with that. So the take-home message is here: if you have a large learner rates, you remember most recent ones. What happened in the past, you forget. If you have a smaller learning rates, the most recent one, it counts, but not counts so much. Instead, what counts is like the accumulated history that had happened in the past. There's a carrying over effect from the past trials. Good. So, like the earlier question is, if we fix our environment to make it stable, and if we also know the reward probability, for example, 80 and 20, and if we also know the number of trials, 100, for example, how can we determine the learning rates? I said the answer is to do a simulation. So how can we do that? Let's say in that kind of scenario, we could if you remember the idea of grade approximation, so we could have, we know learning rates, the positive range, the range of the learning rates is from 0 to 1. So the learning rate alpha, it belongs to a range of 0 to 1. So this is definition. So what we can do is we take small steps. We say we take 0 when learning rate is 0. We do a simulation to ask our model to generate choices, and then to analyze. What we can do is that we analyze the choices that are generated or simulated from the model. So when the learning rate equals 0, we ask the model to select blue and select yellow for 100 times, 100 trials. And we count how often those simulated choices corresponds to the better option. So if, let's say, blue and yellow, the blue one is the better one, from the simulated 100 trials, how often the simulated agent is choosing the blue, okay? And we can do this kind of analysis when learning rate is 0. We can also do the analysis when learning rate is 0.01, 0.02, 0.03, 0.05, 0.06, blah, 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 0.1, 0.1.1, 0.1.2, until the learning rate is 0.99 and 1.0. Okay, this is simulation. And for each of the learning rates, we do simulation, we do the analysis to calculate how often the simulated choices choose the blue one, the blue version. The blue option is the better one. And then we have the data. And then what we can do is we plot it, right? So here, this curve I show you here, this curve is the choice accuracy as a function of all the different learning rates. And if that is a curve, and also if there's a range, it is nearly guaranteed that, well, it's always guaranteed that there's a maximum. Then there's a peak, because it is a closed range. Otherwise, if the range is unclosed, well, maybe there's no positive maximum. But this is a closed range between 0 and 1. We are able to identify or to locate a positive maximum. So in that particular case, what we have seen here, this is the optimal learning rate, because before that, it goes up, and after that, it goes down. That means this one is the top, right? This is the top. So in this particular case, the optimal learning rate is a 0.18, okay? 0.18 in this case. And you can do the similar simulation idea when there are maybe 20 trials, and when the reward probability is, for example, 0.7, 0.3, and when you have, rather than a fixed constant learning reward probability, you have a reversal learning. And using the reversal learning, what the optimal learning rate can be. You can also determine that from this similar approach simulation here, in other words. Does that make sense? Or questions? All good? Okay. So in the next 15, 16 minutes, we then have to go through the next part, like the choice rule, the observation model. So how can we actually link the value updates to the actual choice? So how do we predict that? So what is the actual linking function that I still haven't told you? So we have the choices, blue, yellow, and we have the feedback, win and loss. And we know that there is a Rescorla-Wagner value update rule, and then there's a free parameter, the learning rates. So that means per trial, on a trial by trial basis, we have the value of the blue option, and we have the value of the yellow option. And I was alluring you this idea already, that how can we convert or translate the value of the blue and yellow to the probability of choosing blue and the probability of choosing yellow. It turns out that there are multiple ways to do it. So the first one is called a greedy function. So what is a greedy learning rule? Greedy learning rule basically means as long as the value of blue is larger than value of yellow, no matter how large. Maybe this is maybe this is 0.93, this is 0.928. The difference is super tiny, right? But as long as this one is larger than that, you choose blue. There's no uncertainty. You just choose this. So this is called greedy rule. Greedy basically means you always choose the better one. You always choose the one that you think that will return you a reward. So graphically, what that means the x-axis is the value difference, the value of blue minus the value of yellow. So it doesn't matter the difference, how large or how small that is, you always choose the one that has a larger value. So probability of one of choosing it. But maybe you think it doesn't make sense because if they are super close to each other, one is 0.3, the other one is 0.34. So just slightly better. Or the other example I gave you, what did I say? 0.93 and 0.928, whatever, the small difference. They are close. Both are equally good. Why I choose the one that is better? Maybe the other one is also good, right? So this is not so ideal. And then researchers, they also realize that this twice rule is not so ideal. And then they come up with another version, which basically adds a little bit more randomness or noise to the twice rule. So how does that look like? A similar idea, but then the curve, if you look at the difference like visually, a little bit. So what is changed is the magnitude here, is the magnitude. This one is not 1.0 anymore. It is something slightly below 1.0. So what does that mean? That means most of the time, if value of A is larger than value of B, I have a large probability of choosing value, the option of A. Because A is better, I choose it with maybe 90% of the time. But the 10% of the time, the remaining 10% of the time, I will choose the opposite. Then to leave a little bit room for the randomness to explore the unchosen one, to explore the one that is currently having a lower value, but potentially, who knows, in the future, that one will become better. So it's not so much greedy. So this is called the epsilon greedy. Epsilon here basically means kind of a noise. So when the value of A is larger than value of B, I choose A most of the time, but I have a smaller noise to choose the other one. So here epsilon basically determines the randomness, how often you switch to the other one, that you choose not according to your current valuation. But you would imagine that this is also not so great because here still, even though there's some randomness, still the difference doesn't really make any impact to the choice. So the original scenario that I told you, 0.3 versus 0.31, this still really, there's no difference in choosing. Let me give you another example. So 0.3 versus 0.31 versus another scenario, 0.3 and 0.7, okay? So one case, the difference is small, and the other one, the difference is large, but this cannot be reflected on the curve, okay? But maybe we want something like, we know this is the value of difference, the value of difference, similar as this graph. We want something that if the difference is small, then the probability of choosing or favoring V of A is also small. But when the difference is large, then maybe I will be more likely to choose that one, right? We want something like this. We want to have a curve rather than a fixed or constant line that we have seen here in the current place. So we want something better that can be able to reflect the difference. So it turns out that a softmax function could be able to achieve this goal. So this is a little bit noisy, but we can just look at one curve. So let's look at this curve. Let's look at this curve. Okay, so here from the positive domain, we can see that when the value difference is 0, the probability of choosing A is 0.5. So when the value of two of the choice options, they are equal to each other. Maybe choosing any of them is the same. So 0.5 choice probability, so choosing probability. But when the value difference is large, maybe 1.5, for example, here, the V of A minus V of B is 1.5, then you are really more likely to choose A, okay? And when the value difference is small here, it is larger than 0.5, but not so much larger than 0.5. So here, the value difference really makes impact. So it can be translated to a differentiate effect relative to the probability of choosing A and the probability of choosing B, okay? So here we have this kind of curves, but at the same time, there is a slope, right? We can also have this kind of curve. We can also have this kind of curve. We could also have a flat line, right? All of them, they are kind of like showed here. There's the slope. So the steepness, okay, the steepness is something that we have to consider. So what is that? That is the parameter. That is another parameter in the model that we have to consider and to estimate from the data. So here, when the parameter, the slope parameter is large, it's 5, it is much more steeper. And when the slope is small, it is not so steep. It's like this line. And the extreme case is that I can tell you. So when the tau, this is tau parameter, when that equals 0, this is a flat line. So no matter what you learn, no matter the value differences, everything is 0.5, 0.5, okay? And another scenario is when the tau parameter is positive infinity, then this curve is like a step function, okay? This is step function. And what is this? If you still remember from the 2 slides back, that is a greedy rule, okay? So when the tau parameter is positive infinity, the learning choice rule becomes a greedy rule. And that's reflects or can be linked to what we know already in the literature 2 slides back. So if you want to know the detail, I will skip that a little bit. So the softmax function can be written in this way. So here the tau is how actually everything or the shape of the curve, how that changes. If this tau is large, equals 5, for example, that is the darker purple. If the tau is small, 0.3, for instance, that is this curve, so the slope. Again, the take-home message is when the tau is large, it is more sensitive to value difference. When the tau is small, it is not so sensitive to the value difference. In fact, it becomes much more randomness, okay? You remember that is enough. Questions? Does this make sense or anything? I'm not sure, any feedback? Do you think this is too much to know or just I can skip it? I think I spent too much time in the details. At the same time, I don't know if you get it or not. Right. Good. So there's some kind of combination comparison regarding the 3 choice rules, right? So one is the greedy, the other one is the E greedy, like epsilon greedy, and then the third one is the softmax choice rule. So let's say there's some data. Doesn't matter what the data, where the data comes from. On the x-axis is the money, the monetary money, and just points, cents, 5 and 6 and 9, and then until 16. And then the y-axis is the probability of choosing that one. So the actual data is like shown in black, because that makes sense, right? If the money is not so much, you don't want to choose it. And as long as the monetary unit gets increased, you do want to change it more likely. But if we want to fit the model, estimate the model, if we want to use a mathematical equation to explain the data. So in blue curve, that is the E greedy, epsilon greedy. So we have most of the time 90, as long as the value difference is positive, we have the probability to choose it 0.9. And then there is a small probability to choose another. And in the literature, the E-greedy is kind of a trampling hand model, because most of the time you select the one that is better, but maybe your hand is trembling and you choose the other option, okay? And the red curve is basically the softmax. And what you can see is like, because we do want to have a model that is able to reflect the value difference. When the value difference is small, maybe we choose it maybe around a chance level. And when the value difference is large, we will make the choice, make the decision more according to the value difference. And in that case, we can compare the model prediction, the red dots versus the black dots, which is the real data. You see that really the softmax choice rule is better. So that's why we don't really use, I think nowadays nobody uses the greedy rule and epsilon greedy rules anymore in their choice rule. So nearly all the people in at least decision neuroscience, because this is binary decisions, at least in the decision neuroscience field, nearly everyone is using the softmax choice rule. And there are some improvements recently, but the standard or the baseline is the softmax choice function. Good. So now that everything is complete, we have the value updates, the cognitive model, the value update from the Rescorla-Wagner rule. We have the reward predictor calculation, and we have the value updated from the learning rate weighted reward predictor, and we have one free parameter here, the alpha, and how to connect the value with the choice. We use the softmax or sigmoid curve, because this is S-shaped. Any S-shaped curve is called a sigmoid curve, okay? Don't get confused in the literature. Right? In the literature, in the paper, people say, well, we use a sigmoid function to fit this, to fit that. What is sigmoid function? It has a S shape. Anything has an S shape that is a sigmoid function. No specific meaning. Many functions could have S shape. Sigmoid is just to describe the shape. It is not even precise. Softmax is not so ambiguous. Softmax, there is a specific way to quantify the softmax function. So here, this is what I show you from the previous slides. The softmax choice function is able to reflect the value difference. So the pre-parameter here is the tau. So the slope, how steep that is, or maybe how shallow that is in terms of the value, in terms of which or how large the tau parameter is. So now to try to put everything together. So we have multiple terms here, right? So what is R? R is the data. R is the 1 or -1, whether it is a win or a loss. So this is the data. So what is the V? The V is not a free parameter. This is a variable. It is calculated trial by trial. It has a starting point, 0. And it changes according to the rule here. So the learning rule, we have the prediction error, but the learning rate, this is a free parameter. We don't know it, we have to estimate it from model estimation. And here, what term do we have? We have P means probability, and C means choice. And here, the small a or small b means 1 or 2, blue, yellow. This is the identity of the action, the identity of the option. So here, what is that? The data, right? The data we know on each trial which participants chose. And here, 1 is just number, and E, this is like a constant number. We know that. And the value of B and the value of A is calculated from here. There's a variable. And what's the tau? The tau is a free parameter. So if you want to kind of memorize all of the terms, alpha is a learning rate free parameter, PE is a variable, the value is also a variable, the R reward, that's a data, and then the tau, that is a softmax free parameter, okay? So we have this kind of terms. And when everything are ready, we know what they means and we know what they represent to, we are able to code it in the model. Okay, so that is the implementation, I guess, for the next week. But before that, let me just try to give you the idea that the reinforcement learning framework is pretty powerful to study decision-making, and it can be used in many scenarios. It can be more generalized. So how can we generalize it? what is the prerequisite to be able to use or to be able to apply reinforcement learning models? It turns out that it's not so strict. So what we need to have action, okay? We need to have action. We need to have the outcome or feedback. That's it. This is the prerequisite. As long as you have, you ask participants to make some choices, to make some predictions, to make some decisions in the task, and you also show the corresponding feedback or outcome associated with that action. So they know their consequence. They make a button press, they know what the consequence is associated with that button press. Then you are able to use the reinforcement learning framework. As simple as that, because that is feedback learning, right? Feedback learning means you need feedback. And if you have feedback, then you can use reinforcement learning model. It's really straightforward. So a few examples that can be like this. I should quickly show you this. Symbols and make a decision. So in this case, we can already imagine to use reinforcement learning framework. But here in this case, there's kind of context. One is a win context. You either win or get nothing, or maybe you also have a punishment context. You can lose or you get nothing. You can't win. And then they studied how reinforcement learning changes, how the parameter changes according to the context, reward context versus punishment context. And here again, like symbols, right? Two symbols, you make a choice and you see the outcome. But the experimental manipulation here is whatever you earn, the money or points, whatever money you earn by doing this, you get the money. But in this case, whatever you earn from experiments, the money, the points, they don't give, they're not given to you. They are given to your close friends or family members, for example. So they call that pro-social learning because you make decisions. It's not benefiting directly yourself, but instead your action will benefit other people. And as a control study, two symbols, you can still learn, you can still get some money, but even you perform very well, nothing will be given to anyone. So this is kind of a control. So no one gets the points you earn from experiments. In this scenario, people maybe just don't learn very well because if they learn well versus if they don't learn well, nothing will be changed, right? So this can be compared. Action and feedback, action and feedback, action and feedback. Here, those are a little bit difficult to explain to you within 1 minute, so I will just skip. But these are the links and you can click and look at the paper. The summary is, let me repeat, as long as you have participants in your task, they make action, they observe the corresponding consequence of their action, you are able to use reinforcement learning. This is take-home message from today. Any questions? Yeah. I can stop here. All right, good. And I think if you have no questions, don't forget your login and don't forget the Sunday deadline for submitting your review comments as a PDF file. Next week, we have like shorter session. We have to finish at 2:30. Then see you next week, I guess, if no more questions. Bye-bye.
Bye. Thanks.